So in this section, we'll talk briefly about two important deviations from Ohm's law and the behavior that we introduced in the introduction to drift transport. So first, we'll introduce what really happens as a function of high electric fields. So if we plot the log of the E field, if we plot the velocity as a function of the log of the E field, what's found is that for most semiconductors, a curve like this is obtained, with the rollover point being somewhere around 10 to the 7 centimeters per second. So this is important because this is actually a deviation from Ohm's law. On this graph, we saw that the statement that velocity drift is mobility times E field is equivalent to V equals IR. So in this region here, where we have a constant or nearly constant slope, we're actually obeying Ohm's law. But out in this region here, the velocity is no longer proportional to the E field. It's constant. So what's happening? What changed and what caused this physics? And then furthermore, some semiconductors, especially, for example, gallium arsenide and indium phosphide, actually show a phenomenon called velocity overshoot. And in this case, if you take the slope here, it's actually negative, which means that the resistance here is apparently negative. So this phenomenon is called negative differential resistance. So why do these two phenomena happen? So far, we've talked about the velocity of the electrons and its scattering in terms of the variables of position, velocity, acceleration, etc. But for these two phenomena of the velocity, saturation, and overshoot, we need to think in terms of the kinetic energy. So first, let's check back with the thermal kinetic energy. So we have 3/2 kBt, which at room temperature is about 39 MeV. Now, at very high velocities, the kinetic energy is going to exceed the thermal energy. So the thermal velocity turns out to be approximately equal to that same limit, about 10 to the 7 centimeters per second. The comparison needs to be when our drift velocity is about equal to the thermal velocity, or when our kinetic energy is approximately equal to the thermal energy. And when this happens, we will disturb the population of electrons or holes and start to have the ability to have new physics happening. So to explain first the velocity saturation, when an electron is going so fast in the lattice that it's in excess of the thermal velocity, it's actually hotter, in a sense, than the underlying lattice. So when it slams into or scatters off of an atom, its energy is actually higher than the thermal energy of the atom. And so the probability is that it will actually give some energy, a little packet of kinetic energy will be transferred to the atom, which results in it shaking harder. So this is actually the phenomenon of emission of phonons. So this can explain why the velocity saturates versus E field at about this thermal energy. So as the electron is being accelerated faster and faster by the E field, it'll emit more and more phonons and give off more and more of these packets of kinetic energy. And those competing forces of the accelerating force of the E field and the emission of kinetic energy to optical phonons balance, resulting again in a saturation. So why is this velocity saturation important? Well, let's look at a modern day schematic MOSFET here. So we have our source and drain and our channel in between. And the channel lengths in modern devices are 10 nanometers or smaller. So if we apply a source to drain voltage that's somewhere in the range of 0.1 to 1 volt, what's the E field that occurs in this channel? Well, let's say we have 1 volt over 10 nanometers. So we have 10 times minus 7 centimeters, 1 over that. So our E field is 10 to the 6 volts per centimeter. So at this end of 0.1 volts, we would get 10 to the 5. So we're actually well within this range where velocity saturation becomes important. In fact, in the most smallest scaled devices today, we might actually be in what's called the ballistic regime. So in the ballistic regime, the idea is that the distance you're traveling through this channel, the channel length, is actually shorter than the mean free path. So if an electron starts out at the source and tries to make it to the drain, the probability that it will collide with some atom impurity or some phonon inside the channel is actually smaller than 1. So there may be 0 collisions between the source and the drain. And in this case, the transport can no longer be described, again, can no longer be described by Ohm's law. Instead, it would behave as if it was a free particle in space and not colliding. So we would actually recover the behavior of force equals ma, although the details do become more complicated. So finally, let's revisit the velocity overshoot and negative differential resistance, which we saw on the velocity versus log E field curve. So we have the ohmic region, and for materials like silicon, the behavior is like this, but for some materials like gallium arsenide or indium phosphide, we're talking about this region here. So why does this happen? So now we have to go back to the EK diagram and the details of the different minima in the band structure. So for a direct gap material like gallium arsenide or indium phosphide, the lowest conduction band minimum occurs at the gamma point. And this is where the electrons usually hang out. And most of the behavior in this low field regime will occur there. However, there's other higher band minima that might occur away from the center of the Brillouin zone at the X point, let's say, and at the L point. So now, if we look carefully here, we actually see that there's a certain energy difference between the gamma point and this X point or this L point. And if we think about the kinetic energy of the electron, as it goes faster and faster, this kinetic energy will increase, and you'll be moving up on this EK diagram to fill states here. So the scattering events will take you back over here, but eventually, at high enough electric field, you'll be close enough to reach or exceed this energy difference. And when that happens, you can actually get electron transfer from the gamma valley over to the X valley. Now the thing about this is that M star gamma is a lot smaller than M star X or M star L. So if we write the mobility statement, so the velocity might be the mobility for the gamma point times E if you're in the gamma point. And if we remember that the mobility is E tau over M star, so the M star gamma is about equal to 0.06 for gallium arsenide, and M star at one of these other points, let's say X, might be 0.1 to 0.3 times the electron mass. So that means the mobility here is going to be lower. So when we make this transfer, we're also transferring from this high mobility to low mobility. And what that means is the velocity will actually decrease, as in this section here. So it was increasing, and then we transfer from the gamma to the X valley, and it actually slows down. So that's the phenomena of negative differential resistance. And if you have negative differential resistance, it means that your Ohm's law is broken. You're no longer having the current proportional to the applied E field or voltage. And if you have that happen, you can actually make oscillators and things like microwave sources. So in this short section, we've just investigated 3 different phenomena which are important today because they represent deviations from the traditional transport equations, where the velocity is no longer proportional to the electric field, and thus Ohm's law is not obeyed.